Hello, I'm Isaac, a tutor at CWI, and today I'm going to be working through a problem from homework from Chapter 30. The problem is 26, and it kicked my ass pretty good, so I'm going to go ahead and walk through what I learned. The first part of the problem isn't too bad. What it is saying is that we have a semicircular length of wire, and it's rotating with some constant angular frequency of 4 pi radians per second. And on half of this playing field, we have a constant magnetic field of 1.3 Tesla. And so right away we recognize this is a Faraday's law problem, and so we write it out. We say the voltage induced is equal to negative the number of coils in the loop times the change in magnetic flux with respect to time. Now, we know that this only has one loop, so in other words, n is just 1. So that takes care of that. Usually with these problems, what we're going to do is we're going to write flux of B differently. So I'm going to say this is equivalent to negative the time derivative of double integral of B dot dA. The reason why I say that is because this is just another way to write flux, right? It's the B field that's penetrating the surface A. So that's the second step of this first part. That's equal to V induced. What do we know about B? Well, we know it's constant. It's 1.3 Tesla everywhere. And so it doesn't change with respect to dA. So we can pull B out and take the integral of dA, which is A. But remember, this is a dot product in here, so got to have cosine theta written down. So we've gotten this nice and simplified so far. Alright, we know B. Do we know A? Okay, A is a little bit tricky. A is going to be the area of this semicircle. So it's a half a circle. So we know that A is going to be regular circle, pi r squared, divided in half. So A is pi r squared divided by 2. B is 1.3 Tesla. Theta is another trick. Okay, so we know the angular frequency is 4 pi rads per second. And just like x equals vx times t, so in other words, displacement equals velocity times time, we can also say that theta is equal to omega times time. And so we're going to go ahead and substitute that in here. And so now instead of cosine of theta, we're going to have cosine of omega times time. And that's going to make it possible for us to take the time derivative. So now that we have it at this stage, let's go ahead and take the time derivative. B and A are constant. The derivative of cosine is negative sine, but there's a negative out here, so that'll cancel. So we have sine of omega t, and we have to do the chain rule, so we have to multiply the outside by omega. So we have B times A times omega times sine of omega t. And that is our V induced. All right. Let's go ahead and plug in our values so we can get some sort of a function. So V induced is equal to, let's solve for area. So if the radius is 0.25 meters, 0.25 squared times pi divided by 2 equals 0.25 squared times pi divided by 2. Well, let's write it, because 0.25 squared is going to be 0.065, which is equivalent to 1/8, I believe. 1/4 squared. Yeah, 1/8. So this is going to equal pi eighths divide 2. We can flip that, so this area is roughly pi 16ths. Pi 16ths is what area is equal to. Just going to check that real quick one more time. Pi 16ths. Alright, that doesn't seem to be right. Anyways, we'll just leave it in this form for now. So I'll plug it in, and B is 1.3 Tesla times area, which is pi times 0.25 squared over 2. I don't know why I'm having such a hard time with this little piece of math. Then omega is 4 pi rads per second. 4 pi rads per second. Then we're doing cosine of omega, which is 4 pi rads per second times time. So this is our formula for if we want to know what voltage is at any given point in time. We're going to use this formula to figure out what that is. So let's go ahead and simplify it. And what I'm going to do is I'm actually just going to write down a plain old number, a rounded number. And what I get is I get for V induced, my amplitude is roughly equal to 1.6 times cosine of 4 pi t. I'm going to leave this as 4 pi. So right off the bat, we know here that our amplitude, which is our maximum, we know that our V maximum is going to roughly equal 1.6 volts. So there's part A. And then what's kind of tricky about this problem is the next section. Alright, so the next section, now that we have this formula, I'm going to erase all the work we did to get here. The next part asks what the average voltage is during this process. And so what you have to imagine is like a side view of this loop, this half loop. And so it's spinning this way, right? And we have, let's see if I can find red. We have this B field pointing up on 1/2 of the thing, right? So as this rotates up to vertical, there's actually no B field on this side, so there's no induced voltage. Once it gets to the top, though, and starts going down, you'll notice the flux of B through A's surface is increasing until it's halfway through the B field. Then the flux starts decreasing. And we know that induced voltage opposes the change of magnetic flux. And so if magnetic flux here is increasing, that means that voltage induced will be high in the opposite direction. And then at this point, there's no change in flux. And then as we rotate down, there's a decrease in flux, so the voltage opposes that. And what you end up with is a graph of voltage induced as a function of time that looks something like this. For the first quarter, there's nothing. Then there's a large opposing voltage. So for the first quarter, there's nothing. Then there's a large opposing voltage. Then that voltage decreases to 0 when it's at the horizontal. And then it also, it'll increase again to a maximum right as B goes out of the B field. I'm sorry, right as the coil goes out of the B field. And so what you'll find is this is at the 1/4 of a cycle point, and that this is at 3/4 or 3/4 of a cycle. And we haven't calculated how long a cycle is just yet. but it's actually not really too important, simply because you'll notice that there's an even amount of induced voltage on either side. So if we're going to average this out, the average, and this is part B, so this is part A we solved for here. Part B asks what the average was, the average induced voltage. And if you notice, there's just as much above the curve as there is beneath the curve. And so the V average is going to equal 0 volts. And once you figure out this part, the second part of the problem is pretty easy. Just remember that this formula that we calculated, think about it like this. If I drop this marker, it's going to fall to the ground and stop. But if I apply the equations of motion to this marker, it will fall through the floor and just keep falling. And so essentially mathematical models don't care about boundary conditions. So it's up to us to enforce the boundary conditions. And for this one, the boundary conditions were, if you're on this side of the coil, there's no B fields, there's no induced voltage. There's no induced voltage till we get to here, and then the induced voltage is at a maximum until it gets to 0, and then it's at a minimum. And so that's our job to figure out when that happens. But this model right here doesn't actually cut off where we cut it off at. This model, this equation, doesn't know the boundary conditions, so it'll just keep going. And that's what part 2 is about figuring out what if there was a B field on both sides, then what would happen. And so yeah, I hope this was helpful. It's a really tricky problem. Have a great day.